Welcome to the final session of SANE. Call to order, everybody please come in. Very happy to introduce Wenwu Wang, who is a professor of signal processing and machine learning at University of Surrey. And he has a very broad body of work spanning everything from event detection to source separation and audiovisual processing. And so excited to hear his talk on text and audio for capturing and generation. So I'll take it away, Wenwu.
Okay. All right, yeah, thank you very much for the kind introduction. And I wish to thank the organizing committee for inviting me to speak here. I'm sorry for being unable to attend on site. So my talk is on audio text learning for automated audio captioning and generation. So, this work is funded by British Council and also APSOC of the UK. So this is a joint work with many people here at Surrey and also some external people. There's many PhD students and postdocs, and also my colleagues. Professor Mark Plumley is here on site. So some other colleagues also attending the same workshop today. So here, this outline of my presentation. So I start with a very brief recap about the sound recognition work in the DKS community, and then we will focus on audio to text generation. This is audio captioning work we have done. I can only present selective work here, and also text to audio generation. Finally, we provide a very brief perspective on audio language learning, and then we will conclude the talk. So sound recognition has been studied for a number of years now, and especially since the work from DKS community, the DKS challenge in 2013. So our initial work has been on scene classification and audio tagging and sound event detection. So scene classification is about classifying what acoustic scenes that the recording is taking, and audio tagging is about label the data based on the events or acoustic scenes, and sound event detection is about detecting the acoustic event and the classes and also the onset and offset time of the acoustic events. And just point out one of the work is widely cited work, PANS, we have done here at Surrey. So this is a model trained based on the audio set dataset. And because this is probably the first work that we have done in terms of using the large scale data, the audio set, to train the model. So the performance given by this model was the state of the art, of course. Now there's many more models emerging in the community. So I'll just give you some flavor about how good the model is. Here we have a demo. Is to show that the sound event classified by this model, and here this is sound event, and these are the probabilities estimated by the model. So we can have a listen to this demo. You go hard, you gotta get on the floor. If you want life,
Okay, no more. No more. Okay.
Horse.
A high school girl's been murdered. Mr. Harrison's daughter is missing. And
Okay, what's happening right now in the community? So there's an emerging trend on developing these representation models based on unlabeled data using self-supervised learning techniques. Here we listing a few methods, which is you can see from the literature. Some of them are getting popular. In terms of the mean average precision that can be achieved with these models, for example, BEAT, now it can achieve MAP for the sound event classification task is up to 50. So these results achieved 6 years ago. So there's a significant improvement in terms of the models we can do now. Now I start to discuss the cross-modal translation between audio and text. The first task is audio to text generation. So this is also known as automated audio captioning in the literature. So this is a task, try to generating natural language descriptions given an audio clip. So here we have audio clips. So that's the language description for this audio clip. So we try to develop this automated audio captioning system to describe the audio content. So this task requires the understanding of the audio events, acoustic scenes within the audio clip, and also the relationship, spatial temporal relation between the acoustic event. And then we describe that using natural language. This could be used in a number of applications, for example, in audio retrieval. Conventionally, we use, for example, keywords or audio clips to retrieve the sound clips that are relevant to the keyword or the text or the example audio clips. But if we want to identify the audio clips, which is very close to the precise descriptions of the audio content, then we would have to generate language descriptions to describe the audio content. And in that case, we can actually use such descriptions to retrieve the relevant audio clips from the archive. The other applications including assisting hearing-impaired to understand environmental sound or provide subtitles for sound in TV programs. So this task has started in 2017 and received increasing attention in recent years. For example, in decades challenges in the past 3 or 4 years, we all have these new challenges created for this task. So what's happening in terms of literature and the methodologies that have been developed for this? Often people use this encoder and decoder architecture. So encoder is converting the audio signals into audio features, and the decoder is converting the audio features to language descriptions. And there are a lot of works actually trying on different architecture of encoder and decoder. For example, you have the recurrent neural networks or convolutional neural networks or CRNN or transformer that could be used for encoder. Or for decoder, we have choices like RNN or transformer. There's also a lot of work emerging recently on developing these large language models combined with acoustic models and techniques, for example, contrastive language audio pre-training. So other works are focused on, for example, training methods using cross-entropy training or using reinforcement learning method. And some other works have considered using keywords or text information to improve audio captioning performance or sentence information, and using data augmentation to improve the model performance when the data is limited. So we have a survey paper on this topic. If you're interested, you can read this paper to understand more about the literature. Here we have an example to explain how this works. This is a CNN and transformer-based architecture. So the encoder is based on CNN, is converting the audio signals into more compact embeddings, audio latent representations. And then the decoder, this is a dashed box here, is a decoder is try to take these audio features, audio embedding, and then combine with these text embedding. So because in the training stage, we do have this text information. So we can actually use some pre-trained model to convert this into text embedding. And that can then be fused here together here in using, for example, a cross-attention module. So this cross-attention is take, for example, the audio embedding together with this text information here. So here we have used the so-called masked multi-head attention. So this is mainly to mitigate these issues caused by the discrepancy between training and inference. So in training, we have the ground truth audio captions, but in inference stage, we don't have the ground truth. To mitigate the impact of the following words that have impact on the previous words, then we actually mask all the following words. So basically, we are using this autoregressive method to estimate what should be the next words based on the previous word we have already predicted. So it's essentially we are estimating this posterior probability based on the previous words already predicted and all the audio features. So, and the output of this decoder is a joint audio text representation, and followed by the linear layer and soft mask. We get the probabilities for the words to be picked up from the vocabulary. Essentially, we are estimating the probabilities of the words that should be chosen from our vocabulary. We are estimating the probabilities, and for the words that has a higher probability or highest probability, we will pick up that word as the current word in a sentence. So we estimate the word one by one until we finish estimation of all the word in a sentence. So this estimation of the sentences can be compared against the ground truth sentence. So we can learn, for example, using this cross entropy loss function to compare the difference between them. So this is in general how the encoder and decoder structure is used to predict the audio captions given the audio clip. So in terms of the datasets available in the literature, so we have, for example, closed dataset, audio caps, and also some other datasets, specialized datasets. This closed dataset is relatively small, and is only about 6,000 audio clips. Each has 5 reference captions and 15 to 30 seconds long. And audio caps is larger, and we have about 50,000 audio clips in the training set. Each one has only one reference caption, but in the test and the evaluation set, so the validation set and the test set, we have about each audio clips has 5 captions. The performance metrics is basically we have the performance metrics borrowed from natural language processing. For example, Blue, Meter, and RAV. These few metrics are based on the comparison between the n-grams of the predicted captions and the ground truth caption. So, for example, Blue is calculating the weighted geometric mean, and this meter is a harmonic mean of precision recall based on comparison of these n-grams. And we also have the metrics taken from image captioning. For example, CIDR, SPICE, and SPIDER. So SPIDER is a compilation of CIDR and SPICE. And SPICE is measuring the semantic faithfulness to the audio clips. You check whether this language description can be used to describe the content of the audio signal. And the side is look at the syntax information, see whether it's consistent with human language. So SPIDER is the performance metrics used by the DK's challenge to rank the different systems submitted to the challenge. And we also have some other metrics, for example, birth score, sentence per fans. This is a model-based performance metrics. We also have these MBLU, diff, and that actually are used for measuring the diversities of the captions generated. So there are many open problems. For example, still people are developing data sets because the data set available to train audio language models are relatively limited. And how to obtain a better representation for audio text or join audio text. So it's still an open issue. And diversity problem. And so humans tend to use different language to describe, or different words to describe the same audio clip, and how we can generate diverse captions, from the model. And recent work has considered leveraging the capabilities of large language models to improve the acoustic model. Some other works also considered combining with other modalities, for example, images and video. So there are a lot of work, open problems in the literature, but here we actually focus on two pieces of work we have done recently. One is they are both talking about diversity, right? Diversity in audio captioning. So the first work we discuss here is how to generate diverse captions given the same audio clip. So conventional techniques as the encoder-decoder structure we discussed just now. So the captions generated here, we have examples, tend to be very simple and also common. This is for the same audio clip, we have 5 captions for the closed data set. Yeah, this is one example. We can see that there are some diversities for the ground truth audio captions, but for the baseline system, SANE transformer-based system, we can see that the captions tend to be simple and also using common word, right? But this is quite different from how human label the data. So here in this work, we try to develop a system that can actually increase the diversity of the captions generated. So we have developed this conditional GAN model, where this is a baseline system. What we try to do here is we actually incorporate a random vector to modify the embeddings before passing through this transformer decoder. But of course, using these random vectors, we may not be able to generate the captions which matches with what we're expecting, right? So here we actually use 3 components. One is a so-called discriminator to check whether the captions generated is more like a human annotated captions or is machine generated ones, right? Or this is one aspect we called naturalness discriminator. We try to see whether the captions generated is natural or not. And another aspect we are evaluating is the semantic information, whether the captions generated semantically faithful to the audio content. So we can use this cosine similarity to measure the embedding from audio and the embedding from the text descriptions. This give us a probability how likely this match between them. And also we use this language evaluator to check whether the language or whether the syntax information is consistent with human language. So the natural discriminator here we have a bit more information about, how this is done, right? And we can use, for example, pre-trained models for the semantic evaluator. For the language evaluator, we actually use this CIDR matrix. Essentially, we put these three together using this so-called reward function, right? We have three reward components, naturalness, semantics, and also the language evaluating score based on CIDR. And finally, this is, we are actually optimizing this combined reward. And if you look at the result, now this is a baseline system, the result we explained just now. And here's the result from the proposed system. So now you can see that the system is able to capture the semantic information and also improve the diversity if you compare with the baseline system based on SANE and transformer architecture. And these are the scores achieved. These are conventional scores by measuring the quality of the captions, and these actually measuring the diversities. For example, div1 that actually compares, the difference between the n-grams and the total number of words. One means 1 gram. So if we have a higher div1, which means that we have better diversities, and also we can measure the vocabulary size. And if there are more words used, then it tends to give you better diversity. So that's the first work. The second work we have done is, again, is to do with diversity, but it's addressing an issue in terms of the training. For example, most of the system in the literature, when they train the model, they take the audio clips and then map to one of the captions from the dataset. As we explained just now, the colossal dataset, for each audio clip, they have 5 captions. And in training, what people often do is you take the audio clip and then you match with one of the captions, randomly selected. And so this could have a potential issue that, the performance might not be stable. But of course, we could potentially just match each audio clip with all the 5 captions, one by one. Then we get 5 audio caption pairs. But in these 5 audio caption pairs, we have the common audio clips, right? So if you do in this way, then there's also performance degradation about 7.5% in terms of spider, which we have tested. So to address this potential problem in terms of training the audio captioning model, we propose a method called caption feature space regularization. So the idea is that in the first stage, we try to learn proxy caption feature space. We aim to minimize the distance between the different captions belonging to the same audio clip, but maximizing the distance between different captions of different audio clips. So this is done in the caption feature space. And in the second stage, we train the audio captioning model by incorporating this proximate caption feature space information. So how this is done, here we have a bit more information. So this is the model, the baseline model we have explained just now. This can be, for example, the SANE transformer architecture. Basically, we take the audio clip, we try to predict the captions, and then we compare with, for example, the ground truths using the cross entropy loss. But now in this work, we try to actually take these captions. For example, in the training set, we have audio clips, we have the corresponding captions. We take the captions, let's say each patch we have n audio clips. Each audio clips have m captions. in a closed dataset m equal to 5. So I can actually use, for example, bird model, and with this linear mapping, we get this so-called the output of this model that gives us the embedding of the captions, and then we can calculate this so-called G. This is essentially contains the information from the captions. This is the kind of embedding, right? And then we take this mean and also the marks, we put them together. That gives us the so-called proxy embeddings. The proxy embeddings essentially, we use the matrix E to denote that. That actually shows if the captions is belonging to the same clips, then they are more close to each other in the embedding space. And then we actually compare that by, for example, clustering the embeddings belonging to the same audio clips, and we get this centroid of the clusters. And then we can actually compare each of these proxy embedding with the centroid. For example, here, 1 to 1 means the first audio clip, 2 means the second audio clip here, yeah, and the third audio clip. And this second 1, 2, 3 means that first and second and the third captions. And the D1 means that the centroid of the corresponding to the first audio clip, the centroid of the captions. Yeah, we can see that if we do that, we can capture the similarities between the captions that belongs to the same audio clip, because we believe that these captions semantically they describe the similar information in the audio signal. That's why we can actually push them closer to each other in the embedding space. By doing this, we get this similarity matrix, and then we can incorporate into the training process to improve the training of audio captioning model. Now we have this so-called recognition loss. This loss function is comparing this proxy embedding from for the captions predicted and the ground truth captions, which is taken from the training data. So by doing this, we can potentially improve the result. Here we have shown the result on the closed data set. If you look at the spider, here this is the improved model as compared with the baseline here. In terms of the spider, it improves about 1 or 2 points in spider score. And if you look at this, the embeddings for the captions, you can see that the bird embeddings, this is how it looks like. The same color means that the 5 different audio captions belonging to the same audio clip. And here you can see that in the proxy embeddings is the captions are more closely clustered and seems to be better reflecting the information that corresponds to the same audio clip. So for the audio captioning demo, I mean, here this demo is based on the diverse audio captioning dataset. So the work and the system we developed, and also use the wave caps dataset. We trained the model, and here we have some examples to show how good it is in terms of given the audio clips we generate captions.
Then what you might want to do is add just a little bit of oil.
You're pushing it, Professor. All right. Okay. Jerry Coyne is a...
Вот так мы кормим птиц. Adam, what's for breakfast this morning?
Okay, that's some snapshot about the work we've done.
And what you might want to do.
So we have other works also done in this domain. So because of the time limit, we won't be able to discuss more. So next we want to discuss a work we have done on text to audio generation. So text to audio generation is given the text descriptions. This is the task is opposite to the audio captioning task. So given audio captions, we try to generate the audio signals, which is consistent with the description, right? So audio generation can be used in a number of applications. For example, for game development or audio producer, sometimes we want to generate the sound data that can be used for, sound engineering. And movie producers sometimes also want to generate sound. And other applications, for example, for automated content creation and audio book, music albums, for example, we could also use this as a tool to generate additional data for training our models. So this could be used as a tool for data augmentation. There are many related works in audio generation. For example, in 2019, we have done some work on based on text, we generate acoustic scenes. And also we have, in 2019, we have also done other works on based on text, we generate acoustic events. So last year, there were works on text to audio generation. So basically here, the text is more general text descriptions, sentence or paragraphs, for example, diff sound, audio gen. Diff sound is based on diffusion model, but it's done in the original sample domain. And audio gen is based on transformer model. And the making audio is also based on diffusion model. So there are also other relevant work, for example, text to audio, text to music generation. And we're not going through all the details, but just mention the work we have done here at Surrey is audio LDM. So audio LDM is based on so-called clap encoder, which is a contrastive language audio learning model. So that this model is actually pre-trained using audio text pairs. And we actually align the audio and text in one space using this model. For example, we could use a text encoder to convert the text into the embedding space and the audio encoder to convert the audio into the embedding space. And then we map this into the same audio text space. So this is done using some audio text paired data is pre-trained. But here we actually use these pre-trained claps, but then we try to use these audio clips to train the language, to train the latent diffusion model. Here we have a latent diffusion model. So in a training, because we have this clap encoder, we don't need audio text pair anymore in order to train the audio generation model. This, in our case, is a latent diffusion model. So we are actually not using the original diffusion model. We are actually do this in the latent space. So this latent vector Z is, is done using this VAE type of encoder. So basically, in training, we try to process these. We use audio only data. We don't use audio text pair. So because we are using this clap encoder, so the clap encoder essentially already contains the cross-model information. So in the inference stage, once we have this latent diffusion model, so we can actually use this text information, and then we generate this text embedding. This is essentially the embedding from the clap model. So again, this also contains some cross-model information from audio. So we use this as condition information to condition the latent diffusion model, and then in order to be able to learn this, right, to get this Z, which is the audio prior. And then based on this one, we can then generate this log Meyer spectrum, for example, and then vocoder can be used. This can be models for example, HiFi-GAN to generate the audio signals. So the advantage of this model is that it's done in the latent space, so it's computationally efficient, and also we are using this LDM. We are using this CLAP model, so we don't need to use the audio text pairs in order to train the LDM model. So the audio generation model can be trained with audio data only. So we have also tested this model in a number of downstream tasks, for example, audio style transfer, super resolution, or audio inpainting, and it shows very good performance. Here we have some numbers to show the model size. For example, this is a model size, and this is some performance metrics. This is a objective performance metrics for Fred distance. This is a KL divergence and inception score, for example. And these are the subjective performance metrics evaluated by using human listeners, and overall audio quality and the relevance to the audio caption description. Yeah. So we can see that these model given a state-of-the-art result when we publish this paper. So, and this model is relatively efficient to train. You can use a single GPU to train the model. Here we show a demo to see how good it is in terms of the result. So there are many more sound demos on the project website. If you are interested, please go there and have a look. Now I just very briefly, because I don't have enough time to discuss more, but this is another work, is a follow-up work based on audio LDM. So this audio LDM 2 is we submitted recently. And all the code and demos are also released. If you're interested, and check the website. So in this audio LDM 2, we try to actually develop a so-called language of audio representations for any sort of data. And so this is the structure of the model. Basically, we try to actually take the audio or take text information. We create the so-called language audio representations, Y, and then based on this information, we can generate audio data. Right. So here we have more details about how the system works. So in training, for example, we can use audio MAE to generate these so-called component representations or embeddings. And in terms of text information, we can use, for example, T5 model, and we could also use audio, CLAP model to generate these embeddings. We can also use other information, for example, image and video, and then this can be done using this GPT model. And eventually we get these representations, which is relevant to, for example, the audio signals, but is learned from other informations. And then for the generation model, we used a very similar model as in audio LDM. Here, the architecture we use slightly different. We use this transformer ULET. In audio LDM, we use the ULET architecture. Again, we are actually learning this latent diffusion model, right? And also the audio price is also learned using this VAE model. So we're not going to go details. So just mentioning another piece of work is wave journey. So this is a conversational audio generation model where we actually analyze the text descriptions using, for example, ChatGPT type of large language models. And then we have, audio models which can be picked up based on analysis of the text information using the language models. And then we can actually compose the sound using the different acoustic models based on the description of the text information. So this can be used for storytelling, for example, creating audio stories. And the audio LDM2, in terms of the performance, is better than audio LDM, especially for speech sound generation. The audio LDM is very good for audio the sound effect or music, but not as good for intelligible speech. But audio LDM2 is much better on that. And the wave journey is more for this conversational audio for storytelling type of scenario. And so we also have released the code and demos. Just very briefly, what's going on? We are slightly overrun in terms of time. So what's happening in the literature? There's increasing interest in terms of combining language models with acoustic models to solve some of the problem in conventional sound classification or audio tagging tasks. Right? There's also increasing interest in unifying the open-ended tasks with closed-ended tasks. So open-ended task, for example, captioning or question answering. The closed-ended task, for example, classification, audio tagging, this type of task, and it could be done together. And general dependency models based on different type of data, and also the application of such models to other tasks, for example, source separation, interaction with large language models. There's also how to interact with large language models, creating new data sets for audio language cross-modal tasks, and also some other relevant studies in image and video domain. Here we are not particularly following this area, but there are also plenty of work in this area. I'll just show you an example of a language queried audio source separation. So here we have a sound mixture, for example. So if the query is the sound of hitting the keyboard, then that's the output of the model. So we can use the instructions given by humans to be able to separate the sound from sound mixtures. So recently we have extended this work to a full journal paper. And also we have extended to much wider type of sound classes, audio events, music, and speech for speech enhancement, for example. And so this is more kind of a foundational model as compared with the one we published in the interspeech conference paper. And this model is also released the code and also demos you can find from the website. And WaveCaps is a dataset we released in May this year. So this is built based on the full public available data set, but we use ChatGPT to refine the raw descriptions into better quality descriptions. So this is the prompt we have used for generating better descriptions using ChatGPT. So these are different prompts we used based on the characteristics of the captions from these data sets. And this data set now is quite big. It's more than 7,000 hours. So now it's being used by quite a few people. Another piece of work I wish to mention is a recent paper, survey paper on large audio models, including language models. So this paper is a comprehensive review of what's going on in the literature, in the community. So if you're interested, also take a look at this survey paper. And I have discussed quite a lot in a very short time, mostly in a high level. So in terms of future work, I'm particularly interested in leverage the language models and combine with these acoustic models to solve some of the problems in conventional acoustic signal processing. For example, classification and source separation and some of the tasks like retrieval. And in some of the tasks, it can be hard to solve by using the conventional model, but these language models provide some new potentials to address these problems. And I'm also interested in terms of, leveraging data-driven models like learning-based models with physics-based models. For example, some models that can be described using some mathematical equations. So that's all for my talk, and there are some additional links to the code and papers. And thank you very much for your attention.
Let's thank the speaker. Okay, are there any questions from the audience?
Thank you very much, Wenwu. One of the topics you presented many great works. One of them was you described the type of separation. So there were monkeys and keyboards, and you got it to get the key clacking separated. What happens if you ask the system to separate a type of sound that is not present in the mix? So if I asked it to tell me the sound of a cat when the cat was not present, would it try to morph those sounds into the sound of a cat?
In that case, it's probably return, that mixture type of sound. So it's not going to give you the individual sound, because the way how we separate the sound is the estimation of a mask. So we estimate a mask based on the text queries and using this separation network. And if the text queries does not, linked with the acoustic event in the mixture, then this mask estimate will not be accurate. It's going to still give you output, but that output will not be that accurate. It's probably similar to the mixed sound.
So you don't train it with examples where there's a mismatch and maybe the target would be silence or something?
I think there are examples on that. But you mean if there's a sound classes which is not in the trained model, or not in the mixture, yeah. If it's not in mixture, I think it's it's going to give you a noisy mask. because that's the objective we try to learn. So the information, for example, the probabilities for each time frequency point that belonging to a certain, classes is going to be is very small. So potentially, the mask, I think the mask estimate is probably not going to be the one corresponding to any of the sound events. And I suspect it could also be close to, some kind of noise there. Depending on the probability estimated, if the mask is some of the entries in the time frequency mask, if it's a small number, then it could potentially mask the time frequency component or unit in the mixtures. If the probability is high, then you potentially get very high time frequency unit there.
Okay.
Are
there any other?
I see how good it is in terms of separating the sound, which is not in the mixture.
Any other questions? I have one question. So it seems as if the model is able to learn some sort of compositional representation, implicitly learn some kind of compositional representation of the mixture audio, where maybe the individual sounds are represented in a separable way. Have you thought about trying to disentangle the representations so that some of that compositionality is more explicit?
Disentangle between different audio events? Is that what you mean?
Or characteristics of the sounds?
That we haven't done actually. So that's more like you have to create different models to do this entanglement.
I suppose.
Not very sure about that, but
okay.
Is we try to leverage the text information to build these conditional probabilities actually based on the text queries, and then we use this separation network. Try to estimate the mask. So only when you have the information to do with the audio event in the query, you're probably able to separate out that sound. If not, for other type of acoustic event, you might have to use a different query. This again is a kind of preliminary work that we show that there's potential in terms of using the text description to find the audio signals, audio components from the mixed sound. And even though here we are using, for example, the example that we showed just now is only for one particular acoustic event, but it could be done for multiple acoustic events because it depends on the query. But at the moment, the model is tested mostly on small number of acoustic events, for example, 1 or 2 acoustic events. It's not too many simultaneously. If you have a sound mixture which contains a number of acoustic events, that then that's probably the model is still limited. we showed that in terms of these sound classes, now it works pretty well for a number of different classes, including sound effect and music and speech. Yeah, but there's still scope to potentially improve that.
Yeah. Okay. Very, very nice work. Can we thank the speaker again? And we'll move to the next speaker.
Thank
you so much.
Thank you very much.
Thank you.